Hi guys, in this video we'll continue with alkene reactions and we'll pick up where we left off at in the previous video with looking at hydration of alkenes to give alcohols using water, but importantly we must have the H+ catalyst there as well. Now an analogous reaction is reaction with an alcohol in the presence of H+ catalyst. This we'll see will give an ether because the R group will remain on the oxygen, and of course an oxygen with bonded to two carbons is an ether. Okay, we have our outline there, but let's pick up here. And we wanted to predict a product from this reaction. This alkene reacting with aqueous acid looks like a hydration of an alkene, and that is going to give, I'll show the product, but then we need to always think mechanistically. But I can sort of do that in my head, and the product is going to be this alcohol here, a secondary alcohol, and how did we get there? Well, we have the H+ catalyst, H+ and water, right? Water and H+. That's what H3O+ is. Question is, where do we want to make carbocation, left or right of the original alkene? And the answer is left. So we pull away from the left. This is going to hinge away from the left. It's going to hinge up and go make bond to H, leaving the carbon on the left with no pi bond anymore, and it will thus be a carbocation. So pull away from the left, and that gives boom, 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 boom. New bond to H on the end. That's what that means. Okay, two carbons. All right, we have a pi bond. We have double bond, but the pi bond, one of the bonds, hinges away and makes bond to H. This is now bonded to an H. Okay, the carbon on the right is bonded to the H. The carbon on the left no longer has the pi bond. It's missing a bond. It's now a positive charge. That's what that arrow means. That's what we just did. There's our bond to the H. I can highlight that bond, and there's our positive charge, carbocation. Yes, the next step, just like we draw above, right here, the next step is water attacks the carbocation. Electrons like positive. And that's going to give, okay, oxygen now bonded to carbon. Two H's remain. We don't magically lose H's. One lone pair remains. The other lone pair is now a bonding pair to the carbon, and that is a positive charge. The N carbon still has the new H. I'm no longer going to draw it. There's two H's on the N carbon. The N carbon now has three H's. The next step is we need to lose the H, or H+, to go neutral, and mechanistically something takes it. Well, there has to be a minus here. This is shown very generically, and often it will be generic. This has to be a specific acid. You cannot just use H3O+. You've got to have a minus. Most common is sulfuric acid. So maybe this you use sulfuric acid. And we could use the bisulfate anion to take the H like we did above. But since it's generic, let's just use water to take the H. Okay, there's plenty of water here. There's excess water. This is excess acid typically. These electrons bond to H. This is just a standard acid-base reaction, which we did during test 1. base takes the H, these electrons move on to the oxygen to become the second lone pair. It gives product, but we also form what? H3O plus, reformed, which is essentially acid. There's the H plus again. It's now sitting with water, just like originally the H plus was sitting with water. We reformed that. There's our alcohol. I was able to show it just thinking this in my head because I knew, where do I want to make cation? Left, secondary. I knew water would attack it, and I knew I would lose a proton. But before you get all that clear in your mind, you can work it mechanistically. And your mechanism is just like a formula in a math class. You use a formula to arrive at the product. You don't just memorize all of your answers. Okay, let's try the next one. This alkene. Alkenes don't react with pure water. They also don't react with pure alcohols. The H of an alcohol and the H of water has the same acidity, essentially. But alkenes will react with H+. And we have an H+ source here. HF is a fairly strong acid. I can show H+. The question is, like before, where do we want to make carbocation? Left or right? And the answer is on the left, so we're going to pull away from the left. Okay, again, we're hinging this way. Pull away from the left, and the right carbon is going to make a bond to the H. Same thing. Now we can't get too used to that. Sometimes we may need to hinge the other way. That's going to give new bond to H here and carbocation there, and that is a tertiary carbocation. That's better than if we made carbocation on the right side. That would have been a secondary carbocation. From there, what can attack the carbocation? Well, as we've said, F- is a poor nucleophile. It will typically never act as a nucleophile in this class. It can in specialized cases, but in this class we will typically never see it do that. That's why HF can be used as a catalyst here. So what other source of electrons are around that can act as a nucleophile? And the answer is ethanol. And the ethanol lone pair attacks. And that's going to give bond to oxygen, but there is an H here and an ethyl. I'm going to draw out the ethyl there. One lone pair remaining, and that is a positive charge. Now we can lose the H to go neutral like we did above. Now what can take the H? Well, the F- will take the H. And these electrons bond to H. These electrons stay behind. And we get our final product. Two lone pairs now. Where did the second lone pair came from? It came from this arrow here. Plus what? What else did we form in this last step of the mechanism? We formed HF. And HF is, well, it's reformed. Thus, it's catalyst. Because definition of catalyst is it promotes the reaction. How did it promote the reaction? It promoted it by providing the H+. If there was no H plus, the reaction would not take place. But then the HF was reformed, and that meets the definition of a catalyst. Now in Gen Chem, you'll learn a catalyst lowers the activation energy. Well, yes, because if it was only ethanol, the activation energy for the pi bond attacking ethanol would be very high. So you got to be careful. It's two different reactions, a reaction with H plus or a reaction with ethanol. Now it doesn't make the reaction with ethanol lower. See, that's sort of a misconception coming out of Gen Chem. You think, well, the acid makes the reaction with ethanol easier. No, it does not. It makes the overall reaction easier. It's totally different. The alkene reacts with the H plus, and the ethanol doesn't react until the second step. Then we reform the acid. And so in this case, we actually made an ether because the oxygen has an R group, because the ethanol, the alcohol, had an R group. Where in the reaction above, the oxygen only had H's. And when you lose one H, you're left with an H, and thus your product is an alcohol. So it's essentially the same reaction, we just use a different nucleophile, water versus alcohol. And so over here, you see that it's just water versus an alcohol. If you use water, you're going to get an alcohol. If you use an alcohol, you're going to get an ether. Both of these reactions are regioselective because we would make tertiary carbocation here and secondary there. Stereochemistry, let's address that here. Start laying some groundwork for our stereochemistry discussion. I'll do that on the scratch paper here. Here's the product above. Now we'll learn that this is a chiral carbon, okay? Chiral. Usually indicated by a star here. We'll learn what that means, but essentially for now, we can have two forms here. Let's show this. I think the best way is for me to just show you the two forms and then explain how we got them. That's a tetrahedral carbon, two in the plane, one forward. I'm going to put the OH forward, okay, and then one back, but back is an H. But we could also have so the OH forward, we could have the OH back. Okay? And these two are enantiomers. Again, we'll learn about that when we get to stereochemistry. Now the question here can be, which one of these will be formed in this reaction? And the answer is both are formed. And why? Well, let's go back to the carbocation. Okay. There it is right there, secondary carbocation. Right number of carbons? Yes, 5 carbons, secondary. Okay. It's just that H is not there. You gotta be careful. It looks like it should be another carbon. Joining the H is actually a little bit funny looking. So I don't have it here. When water attacks this, how does it attack? Well, this is sp2 trigonal planar. Okay, you should know why. And And last time we had our note card with the planar flat, okay, carbocation. How do you attack a carbocation? Okay, you attack it from either side of the plane. If it's like that, you can attack it from the right or the left. Okay? And when you have a gazillion molecules doing this, it's going to be a 50-50 ratio. And that's rounded off, 50-50. It's like if you flipped a coin a billion times, you're probably going to get 50% heads and 50% tails. Okay? Now, of course, this was discussed earlier. On this page here. All right? And you get the two products, like I'm showing you, the two products. Again, because the water attacks, when it attacks it, at that point, you're going to get both. Now we have an intermediate. If that's laying flat, we're talking about top, okay, top or bottom. All right. If it came from the top, the water would be up to give that next intermediate, okay, from top. If it came from the bottom, then we would get that there. And then from there, when we lose proton, we get that product and we get that product. So there's a losing the proton step. Ultimately, the stereochemistry comes from how you attack the carbocation. And it's from either side, 50-50. Okay? It's going to give a racemic mixture, which is 50-50 enantiomers. That is the stereochemical outcome for this reaction. Now, doing that now, as we move forward, more as we get closer to stereochemistry, we'll revisit this. But I always like to do this sort of early to kind of set the stage and to sort of reinforce the idea here. So when we get to it, it's not all brand new and you can start looking ahead a little bit. Okay. What's next on our outline? So 3 was analogous in all respects to 2 above, and so we looked at how we can make ethers from alkenes. Next, we have carbocation rearrangements, ring-forming reactions. Let's see what's next here. And indeed, it's carbocation rearrangements. I'm going to get a fresh copy because the ink sort of bleeds through a little bit. And I don't know how well it's showing up or on the video. Carbocation rearrangements. Okay. Let's look at this reaction here. If you take this alkene with HBr, it looks like we're doing a hydrohalogenation reaction. Up till now, we would expect the product to be that there. This reacts with H+, makes secondary carbocation, bromide attacks there, and we get this product. But actually that's the minor product in this case. The major product has the bromine bonded over, looks like, to this other carbon. So how did that take place? Well, the heading gives you the answer. It's a carbocation rearrangement. And these can either be hydride shifts or alkyl shifts. Let's look at what's going on, and let's proceed by just doing a mechanism. Ultimately, what is the mechanism for forming this product? Well, let's take one step at a time. We've got H+, and the only reaction we know thus far is an alkene of reacting with H+. And we know that we need to form carbocation on the secondary carbon, and so we're going to react. We're going to hinge up like this, leaving the bottom carbon, carbocation, the top carbon bonded to an H. Now, the Br minus, which is here, attack there, we'd get that product. So how do we get this product instead as a major product? Well, what happens is there's an H here. Let's draw it in. These electrons in this sigma bond become attracted to the positive next door. And what happens is those electrons break away, so let's grab them closer to the carbon and let's pull them over here and move them over there. Now the H comes with it. Okay? It's like that H is here, all right? This is the bond to H, okay? The H is on the end there, all right? What I did is these electrons, break them away from this carbon and pull them over and bond them over here. The H nucleus comes with it, okay? Now what happens is if this is positive over here, these electrons start becoming attracted to that positive. And what happens is there's a transition state, but they break free and they move over and bond there. But again, the H nucleus comes with it. This is called a hydride shift. Hydride is essentially H minus I, like bromide. That's bromide. This is called H hydride. And that's essentially what's moving, because the two electrons and the H nucleus are both moving over. The two electrons and the H nucleus. Now, nowhere did we actually form hydride, but it's as if hydride moved over. And that step in the mechanism gives Alright. Now this is where we have to decide what H's we want to draw in. I'm always going to draw in the new H. And we also have to be careful. Free rotation. So I didn't really worry about drawing it up or down. There's free rotation now. Sigma bond. I feel like I want to draw in the other one still. Okay, we had two here, we got two there, but where's the positive charge now? The positive charge is now here. Because that carbon lost the bond. Now you got to know that there's actually two H's here, because there's one there to begin with. So there's two H's here, and there's three there. These are only the H's that were new to that carbon and new to this carbon. Positive charge is here. Now, well, first off, we can label this. That's a 1,2 hydride shift. And why is it called 1, 2? Well, if the carbocation is considered the 1 position, then the next would be a 2. Actually, we need to reverse that. Actually, the 1 is where the H is originally. Then it moves to the next one, and that's 2. If this H had moved to this carbon, that would have been a 1, 2, 3, a 1, 3 hydride shift. But it did not. It moved to the second carbon compared to this one being first. Now later on we may see some 1,3 hydride shifts, and in advanced chemistry sometimes you see some maybe a 1,5 or a 1,6 hydride shift. But the most common, particularly for carbocation rearrangements, are going to be 1,2 hydride shifts. But ultimately we get to kind of where we need to, because we see the bromine is added there. Well, how could it add there? Well, it adds right here. The Br minus then adds to the new carbocation, and that gives you your product. And I've not drawn any of the new H's or any of the H's in. Yes, this carbon has a new H, and that one does too. But you got to know they're there. Why would this want to undergo a hydride shift? Well, look at it. Stability. This is a secondary carbocation. And after the hydride shift, it is now a tertiary. So it's more stable. And so that's why it's called a carbocation rearrangement. The carbocation sort of moved around. But you got to be careful. We don't use mechanism arrows to show where charges move. We use mechanism arrows to show where electrons move. This is sometimes also called a skeletal rearrangement, because the H's and the carbons are sometimes considered sort of the skeleton of the molecule. And one of those H's has been moved over here. Okay, so there's our mechanism. Let's do a reaction coordinate diagram for that. Let's label this as A, B, C, and D. 2 intermediates. We have reaction progress, some type of energy. We can start here with A. Then we react with the H plus to give our first intermediate. B. Then B undergoes a rearrangement, a hydride shift to give C, but C is lower in energy. Then bromide attacks C to give final product, and final product is neutral again, and final product is actually lower in energy than A. We covered that last time of Y. And our reaction goes like this. Okay, a transition state leading to B. Okay, as this attacks the H plus, all right, there's a transition state, bam, leading to B. Then there's a transition state of these electrons moving over. Boom. Moving over there. Then there's a transition state of bromide attacking the carbocation. All right, it takes some energy for the bromide to move and to do this. Here I am, I'm attacking. Oh, that was easy though. It's pretty easy to fall downhill. Rate determining step is going to be your first step. All right, typically forming your carbocation is rate determining step. From there we start falling downhill. Going from B to C, we're going downhill. And from C to D, certainly going downhill. Okay. Now here's what a statement we need to make. Anytime a carbocation can rearrange to a more stable carbocation, always do that in terms of predicting a product. And so we should recognize that, and we should predict that this is going to be the major product. Because we recognize that a carbocation rearrangement will take place. We'll say more going forward. Let's try the one below. Now here it looks like we're hydrating an alkene. We have just aqueous acid. There's no halide. Carbocation should be top or bottom, should be bottom. Water adds, look like we should get this alcohol. All right. But instead we get this alcohol, and the hydroxy group is bonded to this other carbon over here. And actually, if we can see, one of these methyl groups is moved over here to this carbon. Let's show a mechanism for this major product. Well, the first step is H+. We attack. We get this carbocation, much better than a primary. If water attacked here, we would end up getting this product. How does the oxygen attack over here? Well, what happens here is similar to a hydride shift, but instead of an H, one of these methyls breaks away and moves over. So take it, it's bonded there, take it and pull it away, okay, it's bonded to that carbon. Take it and grab these electrons, pull them away and take them and bond them over there. Okay? Now the carbon nucleus here at the end of the bond, okay, when we take these electrons away and pull them over here, the carbon nucleus is still attached with these electrons, so now the carbon nucleus is bonded over here. Okay? There it is originally. Grab them and pull them over. That's what I did with that arrow there. And that's going to give I'll keep that the same, but now there's another methyl here. Now where's the positive charge? Well, it should be over here because this carbon lost a bond. Okay? There's no H on that carbon. There's no undrawn H. You got to recognize that. And this is an alkyl shift. We don't call it an alkylide shift. You could. I have seen that term occasionally, but usually we don't use that term. Instead, we just say alkyl shift, because the carbon and the two electrons are coming over. All right. Now I drew that H in. The next step is now water attacks the carbocation, and that's going to give boom, 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 I'm no longer going to draw in that new H, or that's the original H that was added here. But now we have oxygen and there's two H's here. Right? Addition of water to carbocation. Now we need to lose an H. What can take the H? Well, how about water? We're not really showing any minus here. Take H, electrons stay behind. That's going to give that product, and we're going to reform H3O plus. Catalyst reformed. And there's our product. Do not worry about how the OH is drawn down here versus how I have it up here. It's free rotation, and this is not chiral. If it was chiral, there would be more discussion about this. As long as you have the OH attached to that carbon, you're good. Down here, the H plus is the catalyst. Up top, it was not. We did not reform HBr. And so the major product down here comes from a carbocation rearrangement, which itself comes from an alkyl shift. So one thing about carbocations is they're prone to rearranging. Very prone to rearranging. We went from what? Why did it rearrange? We went from secondary, but now we went to tertiary. Better. It started falling downhill. This is also internal. And internal reactions are super fast. And so if this thing can rearrange and start becoming more stable, it will do that. All right. By the way, how do we get minor products? It all depends on how fast this rearranges. The faster it is, the less likely you are to get this product. If the rearrangement is a little slow, it is possible that water would attack the secondary carbocation, and that would lead to that product. For this particular reaction, it is known that this is indeed the major product. Okay. Hydride shifts, alkyl shifts, ring expansions. Just a fancy alkyl shift. Let's look at this ring expansion. Take this alkene with a cyclobutane, react with HBr. Wow, somehow we get a 5-membered ring. Well, this is clearly a ring expansion. Let's show a mechanism for this. The only reaction we know thus far is alkene reacting with H+. Where we're going to form cation at, top or bottom? That would be bottom. So this is going to hinge away from the bottom and hinge out and attack. Okay? All right. Here's our pi bond. It's going to hinge away here. And this goes to attacks, leaving the bottom carbon without a bond. Now I drew my H+ here. I could have drawn it up here and then it would have been more of a hinge out up. But I'm pulling away from the bottom carbon. Sometimes you write the number of the ring here just to clarify and to keep that straight. So the top carbon bonded to an H positive here. We want to look out for rearrangements. All right. Now if the methyl shifted over, that would give, and I'm going to call that A, that would give that carbocation. This carbon has this methyl. You see, I suspect that many of you are going to be confused that that's just a methyl group up there. See, when I drew that H, it looks funny. See, that carbon has a CH3. One of those H's is drawn in. There's two other H's there. That's just a carbon with a methyl. Well, now we pull another methyl over there, and it's a carbon with two methyls. And we went from secondary to tertiary. That's possible. But this is not getting us to where we need to go. We need a 5-membered ring. Also, I don't see a carbon with outside the ring with two methyls. So while that's possible, it's not the way we want to go. Instead of these electrons moving over, what if we take these electrons, okay, in the 4-membered ring, all right, consider this is a ring over here, 4-membered ring, all right, there was a methyl up there coming off that ring and we moved it over. What if instead we take another bond, all right, and move it over? The bond to this carbon instead of the bond to the upper carbon, and move it over. Let's call that B. That's the A. B is going to give what? The electrons used to be bonded up here. Instead, we took them and moved them over to the next carbon, and so now they're bonded over there. All right, windshield wiper. Back and forth. We moved it over here. That's 4-membered ring, but look, first off, where's the positive charge now? It's right here. But this is now a 5-membered ring. That is a ring expansion by way of a carbocation rearrangement, by way of a alkyl shift. This carbon is no longer bonded to that, but this carbon is now bonded to that carbon. Now if I redraw this as a nice 5-membered ring, it's a cyclopentane with a methyl and a methyl, and that carbon has a positive. Now we can see that we can get home by simply the Br minus that is floating around with the H plus. These electrons just attack there, and bam, there's your product. So a ring expansion. The question that, now this is the preferred product. This is known to be the major preferred product for this reaction. If Br minus had attacked here, and instead of showing mechanism, I can just show it reacting as a reactant, that would end up with here. And this is a minor or not at all. I don't really know the ratio of products here other than that one. It may not be formed at all. The question is, it goes back over here. Why is B a better pathway than A? We made tertiary carbocation. That's also tertiary. Is there any reason why this tertiary carbocation would be favored over this one? And the answer is it's a better sized ring. You remember what's your best size rings? 5 and 6. So this rearranged to give a more thermodynamically favorable, a lower energy ring. So that's why that pathway is favored, and thus why this product is favored. Okay. The one below I want you to do on your own. If we look at it, we see we go from a 7 to a 6. Okay? That would be a ring contraction, obviously. The ring is getting smaller. Looks like we're doing a hydration reaction, ending up with an alcohol. But how do we get there? What's the mechanism? And showing a mechanism like we did above with correct arrow movement, correct use of arrows, is important and will be on your quizzes and tests. And again, I refer you back to the introductory guidelines on proposing and showing correct reaction mechanisms, where I give you some pointers there, some tips. Try this mechanism here on your own, and we'll probably do it in class. Okay. On this next page, we'll be moving ahead, and perhaps I should do this on a next video. I think I will. These two here, which are we're going to see ring forming reactions and also polymerization of alkenes. Probably let's do this on the next video. But let me introduce this homework problem here that you should also be working on at this point. Should be very doable. This shows the conversion of cannabidiol, which is found in the marijuana plant, its conversion to tetrahydrocannabinol, THC, which is the active component of marijuana. Now, this compound is made by the plant. It's not made by magic, but it's made by standard chemistry. And this last reaction to give THC is a pretty typical standard alkene reaction. And it's catalyzed by H+, okay? But it's also an example of a ring-forming reaction. Now again, we'll do ring-forming reactions over here a little bit on the next video. I'll end it there for this video, guys, and we'll pick up here next time.